So overall rules, what if we have to put all these together? We want to say, well, I want to figure out the total strength of intermolecular forces, not just what one or hydrogen bonding or London dispersion are. So here's how to figure it out. So first rule right here, look at the masses. If there's a large difference in molecular mass, London forces are most important, all right? And larger masses result in stronger intermolecular forces, stronger London forces. And so we say a large difference in molecular mass, so we're not talking about like the difference between like somebody has a mass of 20 and 28, but we might be talking about the difference between somebody has a mass of 4 and something that has a mass of 20. And so it's maybe you might even say, there's not really a hard rule on this, but you could say if it's more than double the mass, then you would say that's a large difference in molecular mass. And the one that has the larger mass would have stronger London forces and would have the strongest intermolecular forces. So look at mass first. Now, if the molecular mass is about the same, there's not a big difference. There's not, a giant difference in those here. The next thing you want to look at is does it have hydrogen bonding? If there's hydrogen bonding involved, then the one with hydrogen bonding would have the stronger intermolecular forces. So number one, look at which one's the largest. If there's a big difference in size, the ones that are biggest are going to have the strongest intermolecular forces. Two, if they're about the same mass as each other, then you're going to look at, do they hydrogen bond? If they do hydrogen bond, then they'll have the second strongest intermolecular forces, the strongest of anything that's about the same mass. So if you have three that are sort of roughly tied mass-wise, then the one with the most hydrogen bonding is going to be the one that's the strongest forces. If they're about the same molecular mass and they don't have hydrogen bonding, then you look at the polarity of the molecules. So you look at that delta En. So that's the dipole-dipole forces. And so the greater the dipole-dipole forces, the greater the difference in the polarity of the two atoms in the bond, then the greater the dipole-dipole forces and the stronger the intermolecular forces. And if you have something that has it's about the same size, same mass as the other guys here, and it has no polarity, it's a completely non-polar bond, that would have the weakest intermolecular forces. So a few effects of this. Intermolecular forces in a compound help determine several major properties of the compound. The first one is melting point. Stronger intermolecular forces result in a stronger connection between molecules and therefore higher melting points. If you have several molecules here and they have very, very strong bonds, intermolecular forces between them, not chemical bonds, but intermolecular forces, it's hard for them to be able to start moving around and go from that solid where they're connected together into a liquid form. And so they tend to be stuck together. You have to heat them up more to get them to break apart. So that's number one. Stronger intermolecular forces mean higher melting points. Boiling point, same thing. Stronger intermolecular forces result in higher boiling points because the molecules stick together. If you have a liquid and the molecules have strong intermolecular forces, it's harder for them to escape out into a gas. They don't do that very easily. You have to get them going really, really fast to get them to break those intermolecular forces there. So stronger intermolecular forces means higher boiling point. Next one, evaporation. Weaker intermolecular forces result in molecules escaping more easily and increasing the rate of evaporation. So if you figured out the two substances, one has weaker intermolecular forces, you'd also figure it would evaporate faster if it's a liquid. In addition to having that the one with weaker intermolecular forces would have a lower melting point and a lower boiling point. Viscosity is our next one here. And so viscosity is a liquid's resistance to flow. So for liquids to flow, basically what has to happen, the molecules have to move past one another. And stronger intermolecular forces result in a stronger connection between molecules, which makes it harder for them to flow past each other, which makes it more viscous. And so something like honey, if you try to pour it, it doesn't come out very easily. It pours out very slowly. It's still a liquid, but it pours out very slowly. Those molecules don't slide past each other. In this case, because of the fact that the molecules in honey are very large molecules. Since they're very large molecules, then they have high London forces, and so they stick together really well. And so they don't have very high viscosity. Something like, for example, methanol has much, much lower viscosity because of the fact that it's a much smaller molecule than the molecules in honey. And so as a result, it flows very, very quickly, very easily, very low viscosity. Last one we're going to look at is surface tension. Molecules on the surface of a liquid are pulled inward by the intermolecular forces. And so if you imagine we have a liquid, we have all sorts of molecules in here. So we have all our molecules sort of like this. Just to give you an illustration, I'm just sort of randomly putting them in here, is that if you have these London forces, it's going to attract all these guys. And so the ones that are sort of on the second row are going to get sort of pulled in every which way, right? But the ones on the top only get pulled down. Okay, they only get pulled downward, and so that means your surface molecules always get pulled into the liquid, and the stronger the intermolecular forces, the more tightly they get pulled into the liquid. And so what this does is it means that if you have a liquid that's like laying flat on a surface, and my marker's not working all of a sudden, let's try that again. So if you have a liquid and you try to make it lay flat on a surface, what's going to happen is these molecules on the edge are going to pull inward toward the middle, and it's going to cause that liquid to try to bead up. And the stronger the intermolecular forces, the more it'll bead up. If you have something with very, very weak intermolecular forces, it may not bead up very much. It may be just a little bit like that. But something with very, very strong intermolecular forces, it's going to bead up a whole bunch whenever it's in liquid form like this. And so the stronger the intermolecular forces, the stronger the surface tension, the more the liquid will bead up, the more it'll have a tendency to pull together, like into drops. Like, when water, you have raindrops, it tends to pull together into sort of somewhat spherical drops right here, and that's because those intermolecular forces between the water molecules pull them all towards the center. The stronger those forces, the more likely it is to bead up like this. So let's take a look. Let's rank the following substances by strength of intermolecular force. And so we have C3OH, O2, C2H6, and C8H16. And so remember our rules for trying to rank substances from strongest to weakest intermolecular forces. We first want to look at molecular mass. And if they're the same, we then look at hydrogen bonding. And then if there's no hydrogen bonding, then we look at the dipole forces. We look at how much of a dipole these things are. So first thing we want to do is look at mass. And so let's just write out the masses on each one of these. Once again, we don't have to be super precise. We just need to get a general one. You can, since we're not being exact, it's okay to round to the nearest AMU on this. So C3OH. And so we'll start off doing this one. So it's got 1 carbon, that's 12, plus 4 hydrogens, 3 here and 1 here. So that's a total of 4. Then plus 1 oxygen, which is 16, gives a total mass of 32 for that. O2 is 2 oxygens, so it's 2 16s, also 32. C2H6, so that's 2 times 12 plus 6 for hydrogen, gives you mass of 30. And C8H16, so that's 8 times 12 for carbon plus 16 hydrogens. 16 times 1 is 112. All right, so first thing we're going to look at is size. So is there any one that is clearly the largest? And the answer is yes. C8H16 is the largest, and so this is going to have the largest intermolecular force. We'll put it as number 1 because it has the strongest intermolecular forces. The last 3, though, are about the same in mass, and so we're going to have to look first at do they hydrogen bond. And so to do that, we're going to have to draw out their structure. And so we'll first do our CH3OH. And so of these, the hydrogens only have 1 bond. They can't be in the middle, so we're going to have the carbon here. It's going to have to bond to the oxygen, which has 1 more bond. The carbon should have 3 others. And so, CH3. So those H's go up here. Just like we learned in that structural forming part, the last H right here is going to have to go out here. So is there a likelihood of this hydrogen bonding? So we see H's. There's an H here, and here, and here, and here. These guys only could possibly hydrogen bond if they're attached to a either oxygen, fluorine, or nitrogen. These guys are not, no hydrogen bonds there. This one is attached to oxygen, so we have a chance of hydrogen bonding here. So that one very well could be our second one if none of the other ones have hydrogen bonding. Next one up we're going to look at is O2. O2 is oxygen, so we have 2 oxygens here. Oxygen has 6 valence electrons, wants to get to 8, and so is going to need to share, you get 2 more electrons, and so that means it's going to have to, it has 2 partially filled orbitals in the 2p. It's going to end up sharing 2 pairs of electrons, which means it'll double bond. No hydrogen bonding here because there's no hydrogen. Our last one here is our C2H6, and so we have 2 carbons. They're going to have to be in the middle because the hydrogens have to be on the outside. Do we have 6 spots for hydrogen? Yes, we do. So 1, 2, 3, 4, 5, 6 right there. All right, so of those right here, do we have any hydrogen bonds? The answer is no. We have a bunch of hydrogens, but none of them are attached to nitrogen, oxygen, or fluorine. And so because of that, number 2 is going to have to be this guy right here. And so because it has hydrogen bonding. Third rule we look at is polarity, is that do we have any polar bonds? The one with the most polar bonds is going to be the one that's number 3 on this, the third strongest intermolecular forces. And so the 2 oxygens, they're the same thing. They both have the same electronegativity. That's a completely non-polar bond. So that's, unless the other one has no polarity whatsoever, the O2 is going to be last. That's the weakest intermolecular forces. C2H6, we have connections between carbon and hydrogen. Carbon has an electronegativity of 2.55. Hydrogen is 2.20. While that is considered to be a non-polar bond, it's got a difference of 0.35. 0.35 is bigger than 0, which is the difference in the two oxygens. And so that means that this guy right here is going to have the third strongest intermolecular forces, and the oxygen would have the fourth strongest. And so that's how we work those out. All right, so that's how you figure out the order there. You look at mass first, then you look at is it hydrogen bonding, then you look at which one has more polar bonds. And that'll tell you the order from strongest to weakest intermolecular forces. Next thing, CH4, C4H10, H2, H2O, MgS, SO2. So same thing, we need to figure out first what are our masses. CH4 has 1 carbon and 4 hydrogens. That's carbon is 12, hydrogen is 1, so 12 plus 4 is 16. So the mass is going to be 16 there. C4H10, it's got 4 carbons and 10 hydrogens. So 4 times 12 plus 10 hydrogens, another 10 is 58. So 58 for that one. H2 is 2 hydrogens. That's just going to be 2. H2O is 2 hydrogens, 1 oxygen. Oxygen is 16 plus 2 is 18. MgS, magnesium sulfide. And so magnesium, look at the periodic table, is 24.3. We'll just do 24. Plus sulfur is 32.07 or 32.06. So plus 32 gives up 56 right there. And then SO2, sulfur dioxide, sulfur we says 32 plus another 2 oxygens, which is 2 times 16 is another 32, gives us 64. All right, so first thing, is there clearly a largest one? No, but we have 3. They're all in that sort of largest category. We have a 58, a 56, and a 64, all pretty close to each other. These are going to be the top 3, the ones with the 3 strongest intermolecular forces, but we need to figure out which one is which. So first thing, let's take a look at the C4H10. And so C4H10 doesn't have hydrogen bonds in it. Well, we know it's not. We don't have to draw this out because hydrogen is connected to carbon the whole time. There are no fluorines or oxygens or nitrogen in here, so that one doesn't have hydrogen bonding. MgS, does that have hydrogen bonding? No hydrogens, can't have hydrogen bonding. And the last one's SO2, does that one have hydrogen bonding? Can't have hydrogen bonding because it doesn't have hydrogens. So knock that out. Next rule we're going to look at is going to be, does it look at the polarity? We've got to look and see how polar the bonds are. Well, in the C4H10, there are really only 2 possibilities. Draw that out. Either the carbon is attached to another carbon, and carbon has the same electronegativity as carbon, so that's not polar at all, or it's carbon and hydrogen. And so carbon, we said, is 2.55 for its electronegativity. Hydrogen is 2.2. Take the difference, and it's 0.35. And so for this guy right here, we say 0.35 is the electronegativity difference. MgS, magnesium is 1.31 for electronegativity. Sulfur is 2.58. So you say 2.58 minus 1.31. And so 1.27 is our electronegativity difference for that one. That's a lot higher. And so that's going to be a lot more polar than C4H10 and anything in C4H10. And our last one is SO2. And so for that one is that the sulfur is 2.58 and the oxygen is 3.44. And so that has to be a sulfur-oxygen bond. So then 3.44 for oxygens electronegativity minus 2.58 for sulfurs gives us 0.86. And so of these 3, which are our top 3 candidates, then we're able to say that the one that's the strongest intermolecular forces is the MgS. That'll be number 1. The second strongest is going to be the sulfur dioxide because that's 0.86, and the weakest of these 3 is going to be the C4H10. So that lets us look at the next ones here. So we've got 1, 2, and 3 ranked. So then we're going to look at what's the next one's largest in size. The next one's largest in size, we have a 16 and an 18, both about the same size. And so we're going to have to compare those 2 because they're close to the same size here. The 2 for the hydrogen, much smaller. So we'll leave that alone here. Though I guess at this point we actually know it's going to be last. So we'll get to that one a little bit. So CH4 and H2O. First question we asked, does either one have hydrogen bonds? CH4 has hydrogens, but they can't be attached to nitrogen, fluorine, or oxygen because there is no nitrogen, fluorine, or oxygen, so that doesn't have hydrogen bonds. H2O has hydrogen bonds because we have a hydrogen attached to an oxygen. And so that means that number 4 is going to have to be on the ranking, is going to have to be the H2O, which means number 5 is the CH4, which means number 6 is the H2. And so strongest intermolecular forces is MgS. Second strongest is SO2. Third strongest is C4H10. Fourth strongest H2O. Fifth strongest CH4. Sixth strongest H2. So now our question, rank the following from lowest to highest boiling point. So remember is that whenever a substance has strong intermolecular forces, it's typically going to have a high boiling point. So when we say rank it from lowest to highest boiling point, we're really ranking it from weakest intermolecular forces to strongest intermolecular forces. So let's go through this. First step, as we said, look at the masses. BaCl2 is, taking a look at this right here, Ba has a mass of 137 and plus 2 chlorines, which are each 35. So plus 35 times 2 is 70, is 207. But wait a minute here, Ba and Cl. Let's take a look at the electronegativities on those two guys. Barium has an electronegatividity of 0.89. Chlorine is 3.16. Those are bigger than 2. This is ionically bonded. This wouldn't have any intermolecular forces at all because it should just be alternating barium ions and chlorine ions. So that actually tells us something right off the bat, because if that's true, that it's ionically bonded, that means it's automatically number 1. It's going to have the strongest forces in between, the highest boiling point, because remember that ionic bonds are always stronger than intermolecular forces. So it's a little bit of a trick question there. So we know that one is going to have the highest boiling point. So of these 4, if we're ranking them from lowest to highest boiling point, this one is number 4, which is the highest. And so the highest is 4. Remember, the lowest is going to be 1 right here because we're ranking from low to high. So we know that's going to be there unless any of these other guys are ionic. So we'll see on that. So that might change if one's ionic and if there are 2 ionic ones here. But right now, we're going to say ionic bonded, no intermolecular forces, just ionic bonds, which are automatically stronger and so would result in a higher boiling point, as we learned about in the bonding lesson before. Let's look at our next one, H2. So we're going to toss BaCl out as one that doesn't have intermolecular forces. H2 has 2 H's, which should have a mass of 2. CO, carbon monoxide, 1 carbon and 1 oxygen. Carbon is 12 plus oxygen 16, so roughly 28 for its mass. Once again, we're not being precise, just rounding in general. HF, 1 hydrogen and 1 fluorine, and so that's fluorine has a mass of 19, and so 19 plus 1 is 20. And neon right here is also 20 for its mass. And so let's take a look. So of these remaining ones, of the H2, the CO, HF, and the Ne, are there any one that stands out as far as mass? Not really. We have 3 that are up in that top range, 28, 20, and 20. The 2 is definitely not in that range. So we're going to have to compare those last 3 first to see which one has the strongest forces. And so I guess this automatically means the hydrogen has got to be number 1, because we've already figured out that so the barium chloride is number 4, the strongest forces and the highest boiling point. Hydrogen up to the lowest boiling point because it's not one of those 3. So we need just 2, 3. Actually, that's not 4. I said 4. There are 5 things here, and so that should be 5. I can't count, so that should be 5. So 2 points to you if you caught that. But there were 5 things, not 4. All right, so that's be 5, which right here is we just need to get numbers 2, 3, and 4. And so we have CO, HF, and Ne. First thing we look at is there any hydrogen bonding? And so CO, no hydrogen, so therefore no hydrogen bonding. HF, there is a hydrogen, and it has to be attached to a fluorine. And fluorine is one of the 3 we said, nitrogen, oxygen, or fluorine. So it does have hydrogen bonding, so that's probably going to be our second strongest one here. And so that's probably going to be number 4, because it has the second highest intermolecular forces. But let's check. Neon is our last one. Neon definitely doesn't have any hydrogen bonding because just 1 element, no hydrogen. So that means number 4 is going to be the HF. All right, so that is our second strongest. Third, we are comparing the CO and the Ne. So we asked the question, which one is more polar? So Ne is just 1 atom. It can't be polar. And so CO, if it has any difference in electronegativity, which it does because carbon is 2.55, oxygen is 3.44, it is a polar molecule. So that means next is going to be the CO, then next is going to be the neon, and then last is going to be hydrogen. So ranking them from lowest to highest boiling point, hydrogen would have the lowest boiling point, neon would have the second lowest boiling point, carbon monoxide would be 3rd lowest boiling point, hydrogen fluoride would be the 4th lowest boiling point, and barium chloride would be the 5th lowest boiling point. All right, let's check another one here. CH3, CH3, CH3OH, CH3, CH2OH. So these are long formulas here. We could draw the structural formula, but let's just see if we can figure out what's going to work here just by mass first. So CH3 has 2 carbons, so that's 2 times 12, plus 6 hydrogens, so it gives a total mass of about 30. CH3OH has 1 carbon, that's 12, plus 4 hydrogens, plus 1 oxygen, which is 16, gives us a mass of 32. And then CH3OH has 2 carbons, that's 12 times 2, plus 3 plus 3, 6 of 6 hydrogens, plus 1 oxygen is 16, is 46. All right. So right now, these guys, definitely the 30 and the 32 are about the same size. The last one, the 46, I'm not certain is different enough to make a difference here. So that's probably going to be, that last one is probably going to be the one that's got the strongest intermolecular forces and therefore the highest boiling point. But we need to sort of double check it. So let's take a look at these. And let's assume for right now that they are all the same as far as mass-wise, just because it's not easy to tell exactly. And let's look at the next thing, which is hydrogen bonding. And so do any of these hydrogen bond? Well, number 1 over here definitely does not hydrogen bond because it's got hydrogens but no oxygens, fluorines, or nitrogens. So that's not it. The C3OH is going to probably hydrogen bond because if we draw out the structure on this, we'd say, okay, it's got a C, that's got to connect to the O has got to connect to an H, and then the other 3 go on like this. And so we have an oxygen that's connected, or hydrogen connected to either oxygen, fluorine, or nitrogen. So yes on the hydrogen bonding on this guy. What about our last one? Well, it should be the same thing, is that this one is CH3CH2OH. So we have 2 carbons, 1 oxygen, CH3, they look like this. CH2 goes 2 hydrogens off the carbon, and then 1 out here. We still have hydrogen bonding going on here. And so they both have hydrogen bonding for this guy and for this guy. And so to compare these two, since they both do have hydrogen bonding on here, that's where the mass is probably going to be a difference here. And so we are going to say that this guy, since he's more massive, is going, since they both have hydrogen bonding with this guy, then we would say that our last one here is going to have the highest boiling point. That's going to be number 3. That means then that of the other ones, this one would have to be number 2 because it has hydrogen bonding, where this one does not have hydrogen bonding. So ranking from lowest to highest boiling point, CH3, CH3OH, and then CH2OH in order going 1, 2, 3 from lowest to highest boiling points. So let's rank the following from lowest to highest melting points: CH2H5Cl, C2H5Br, CH4, and C2H6. Same thing, we're going to start off by looking at the masses. And so for the masses here, C2H5Cl, and so that's carbon is 12 times 2, plus 5 hydrogens, plus chlorine, which is 35, gives us a total mass of about 64. Once again, just estimating. C2H5Br got 2 hydrogens, or 2 carbons. 12 times 2 is 24, plus 5 hydrogens, plus a bromine. Bromine has a mass of 79.9, so we'll put in 80, so 109. Then CH4, 1 carbon plus 4 hydrogens, 12 plus 4 is 16. And then C2H6 is going to be 2 carbons, so that's 24. Plus 6 hydrogens, that's going to be 30. So this one's actually should be pretty straightforward because we have pretty much it's halving like every time. So lowest to highest melting points. So the one that's going to have the strongest intermolecular forces, that's the one that would have the highest melting point. And that's going to be number 4, would be our one with the highest mass. So that's number 4 right there. Number 3 would be the one with the second highest mass, which is this one. Because there's a big difference between 3 and 4. There's a big difference between the 16 and the 30 and the 64. So that's going to be number 2. And there's a big difference between the 16 and the 30. So that's number 1. And so, hey, we just got it right there. We don't have to look at anything else. All we have to look at is mass. This one made it clear that the one with the lowest boiling point, the lowest melting point is CH4. The second lowest is C2H6. The third lowest is C2H5Cl. And the fourth lowest is C2H5Br. All right, last one. We're going to rank these PCl3, CL2, MgCl2, and Br2 from lowest to highest melting points. So first thing that probably stands out, that MgCl2, that suspiciously looks like it might be ionic. Let's double check it and see if it is, because if it is, it definitely has the highest melting point. So magnesium is 1.31 for the electronegativity. Chlorine is 3.16, so not quite. It is going to be covalent, but it's very, very polar. So we got to look at our masses again. So let's take a look. PCl3, so we look at phosphorus. Phosphorus is 30.9, so we'll put in just 31 for that. So 31 plus 3 chlorines. So then 3 times chlorine is 35. So that's 136 is the mass of the phosphorus trichloride. And then Cl2 is chlorine. That's 35.5 times 2, so that's what 70.9, so 71 for the mass of that, MgCl2. So trying that one out, so magnesium is 24 plus 2 chlorines, so plus 70.9, so about 95 on that one. And then Br2, 2 bromines, so bromine is about 80, so 80 times 2 is 160. So for our 2 first ones here, we have 2 that are roughly about the same size, the 160 and the 136, and 2 that are about the same size here, the 71 and the 95. Once again, they don't have to be exact, they just have to be sort of in the right range. But there's very clearly a difference between those 2 I circled and the 2 that I boxed. So let's compare the 2 we circled first. Those should have the strongest intermolecular forces and therefore the highest melting points. So PCl3. So the chlorine of those 2 is the more electronegative. It only makes 1 bond anyway. It's going to be the one that's on the outside. So these are all phosphorus chlorine bonds. There's no hydrogen bonding in there because there's no hydrogen. In the Br2, no hydrogen bonding there because there's no hydrogen. So we have to skip that, go to the dipole-dipole forces. So as we said, phosphorus is got an electronegativity of 2.19. Chlorine has an electronegativity of 3.16. So the difference in electronegativity is going to be 3.16 minus 2.19, and so we get 0.97. Okay, for the Br2, well, it's just 2 bromines. They're exactly the same thing, same electronegativity, and so that's got a difference of just 0, and so that's not polar at all. And so that means that of these 2, the 160 and the 136, because they're about the same mass, number 4, the one that's got the highest melting point, is going to be the PCl3. The one that's got the second highest one is going to be the bromine right here. Even though it has a slightly higher mass, is that since it has no polarity at all, but they're close in mass, then we'd say that. So let's look at the next ones. The next 2 are this Cl2 and the MgCl2. So they're about the same size in mass, roughly. Cl2, once again, it's going to have that electronegativity difference is going to be 0 because it's the same thing. No hydrogen bonding in it. We actually should have looked at hydrogen bonding first. There's no hydrogen in MgCl2, so no hydrogen bonding there. So we have to look at that polarity. Is it which one's a dipole? Cl2 is definitely not a dipole. MgCl2 is definitely, we already checked that. It went from 131 for magnesium as the electronegativity to chlorine being 3.16. Those are definitely different. It's going to be definitely bigger than 0, and so that means that that the next strongest is going to be the MgCl2. The weakest is going to be chlorine. So that means the lowest melting point will be for chlorine, Cl2. The second lowest melting point is for MgCl2. The third lowest melting point is going to be for Br2. And the fourth lowest melting point is going to be for PCl3.